All right, sorry about that. So new unit, totally new subject. So before we've been talking about evolutionary optimization, a lot of things inspired by genetic algorithms. So today we start shifting into looking at algorithms that are inspired by other aspects of nature, primarily physics and statistical mechanics. And there's one particular focus here that we're moving up to, and that's the algorithm known as simulated annealing. So we're working up to simulated annealing, which is an older optimization metaheuristic. It is not a population-based metaheuristic. It's a heuristic that you can think about as a single search through a space from one strategy to another, but it has been highly successful. It's a great benchmark. It's still used in a lot of different systems. And now you'll actually find, how many people have heard of D-Wave? They make quantum computers. So there are, or how many people have heard of the Intel Loihi chip for, it's a chip for spiking neural networks. So although this has got old applications, then you see that there are now hardware implementations. And so some of those include D-Wave's quantum annealer. So there's a D-Wave quantum computer. And there are various application-specific integrated circuits that are kind of built for this. And so there's various different hardware solutions. And for example, if you've heard of Intel's Loihi chip, this is a chip that's been built for spiking neural networks, which we'll talk about in a couple of different units, but you can actually co-opt it to do annealing as well. And so you can even use things like Loihi to do annealing on a hardware platform. So, and so those, I'd mentioned like D-Wave in here. And so, so this company has gotten a lot of popularity because they've been able to scale up something that looks like quantum computing. I don't talk about quantum computing much in this class, but it's not really quantum computing. It's just annealing, which is exactly what we'll talk about this unit. It's just having to implement on a substrate that is kind of involves a few kind of quantum effects, but there's nothing really exciting about what D-Wave does. It's just annealing, but they just have built it on a particular hardware platform that's very convenient for it. So learning about annealing is not just a walk through learning about these metaheuristics. It's actually very current because we're seeing a lot of different very modern hardware platforms that make use of this idea. All right, so so to get into that, so that's where we're heading toward. So where does the motivation for this, or what the heck is annealing to begin with? And so we're focusing on physical processes. So this is sort of, this is where we're going. In this unit. But first, let's step back a little bit and think about physical processes in general. And so, like I said, all the things we're going to talk about in this unit, primarily simulated annealing and something called maximum entropy methods, or MaxEnt. So thove of you who've done a little work, maybe in the natural language processing, have a little background in that, you might be familiar with MaxEnt methods. Some of you who've done a little bit of bioinformatics might be familiar with MaxEnt methods. So we're going to talk about where MaxEnt comes from. And so these all have a common inspiration. And so if we think about physical systems, so imagine a physical system. And by a physical system, I mean the tables in front of you, the desks in front of you, maybe at home, yourselves, etc. And so in each one of these physical systems, we are going to talk about the physical system being at a given temperature. Which I'll just refer to as capital T. And if you think about it, even though we experience the world in a lumped model, so that chair that's over there looks like a single chair, this pencil looking thing here looks like a single pencil. Really, it's made up of lots of tiny little components. And those tiny little components are jostling around. And if we had to keep track of where each one of them was, it would make for a very large description space to keep track of every molecule jostling around in every piece of matter. And so that space is the space of what we refer to as microstates. So the physical system has many micro scale configurations. I'll say microscale components that themselves have many degrees of freedom. And I might use the abbreviation DOF when I talk about degrees of freedom. And you can think of these many degrees of freedom as different configurations. Conceptually, it might be easiest to think about positions, but we're also thinking about momenta as well. And so you're not only caring about where every molecule in that chair is at this instant, but how fast each molecule is jostling at any particular moment. So it's a whole lot of information about what's going on to the microscale components in that chair, in this pencil, in me, in you, in the tables around you, and so on. Very high dimensional. Now, some configurations have lower energy than others. So, in other words, if I had a ball, like a big playground ball right in front of me, and I held it up high, it's got high gravitational potential. And if I set it on the ground, it would have lower gravitational potential. If I had a little bit of energy so that it bounced on the ground, then sometimes it would be sitting on the ground with low gravitational potential. Sometimes it would be jostled up into the air with higher gravitational potential. And so you can imagine that's going on at the micro scale and all of these different molecules. And then sometimes the chair, the pencil, et cetera, are sitting just spontaneously in lower energy states than other times. So that's kind of, you can think about there, is how much potential energy do they have in them in each one of these states. Now, the temperature, just like that bouncing ball, if it's got a little bit of a bounce to it, then that temperature is going to prevent them from staying in those lower energy states for long periods of time. They'll be jostled out of it and then they might return. So this temperature T that I'm talking about, so temperature T means systems will spontaneously move into higher energy configurations. With some limit. That little bouncing ball is not suddenly going to bounce up and hit the ceiling if it was just kind of sitting down here bouncing. So somehow there is a notion of the kinetic energy in a system, and that these small scale trade-offs going back and forth between the kinetic energy and the potential energy. And the temperature gives us a way to sort of get an idea of how much energy is just sort of stuck in the system. And that kind of tells us what microstate jumps are possible. So you might imagine if things are really hot, then it is very possible for the microscale analog of the bouncy ball to go all the way to the ceiling and down to the floor and back and forth. But if it's very cold, then that ball is pretty much going to stay towards the ground the whole time. So it's kind of the conceptual analog there. And so what the physicists have done, or what somebody named Boltzmann has done, is they said, we can actually keep track of the average amount of energy in the sort of microstates of a system. And that average amount of energy is going to be proportional to the temperature of the system. And so we have this thing called Boltzmann's constant. or I think it's formally called the Boltzmann Constant, but some people call it Boltzmann's Constant. So you guess you could do apostrophe S if you like. And it's usually just K, and you can look up the values for K. And it is just a conversion. It's a proportionality constant between temperature and average energy of a microstate configuration. To put that a little bit more formally, we can say that the average energy in a physical system. So if I were to average, if I look at all of its possible microstates, sometimes it's in this microstate, sometimes it's in this microstate, and so on, I can say, well, how much energy is in all of these microstates? Take the average across all of them. Because sometimes, it might sometimes be up here, but it's really, really rare. It's usually down here. And so you can kind of weight that by how likely it's going to be there, and you end up getting an average. And that is going to be equal to K times T. And so if you remember back to some of your old physics courses and things like that, or some of you have maybe taken some information theory courses, or maybe some thermodynamics of information courses, things like that, you might see this KT show up. And so KT is kind of like an energy budget for a physical system. It's like, it gives you an idea of the accessible microstates for a given temperature. If T is large, you have a lot more microstates you can spontaneously enter. If T is small, the microstates are less because you just don't have enough energy to get to them. And so another way I could put that, and I hope you can see the optimization starting to creep its way in here, is that, and if not, that's fine. I will be more explicit as we go on here. So the idea here is that if we have some, so as an example, if we have some delta E, which is the change in energy going from one microstate to another. So this is how much is required. So I could say change in energy, I could even put maybe required up here. And because I've written this all in green, maybe I'll put a little box around this. And so that's how much energy is required. That's the cost of the jump. Then the idea here is that if delta E is far less than KT, then jump is likely. And otherwise, if delta E is greater than KT, jump is unlikely. Or if I want to use a banking analogy, we can think of KT as the amount of money in the bank or your budget. So this is your energy budget, and this is the cost of the jump. So if the cost of the jump is less than how much energy you have available in your system, then it's likely you can make the jump. If the cost of the jump is much higher than the amount of energy in your bank account, it's unlikely to make the jump. So that's how this magical quantity KT works. So the idea is, if I want a system to be able to move into other states, I can heat it up. And as I heat it up, it starts to explore more microstates. Now, it won't stay in any of those microstates for very long. So it will, so if I heat to high temperatures, it will often be far from its minimum energy level. But if I cool it down to low temperatures, it won't move very far. Now, all systems will tend towards their lower energy level. So this chair, if you come back in a million years, will probably not look like this chair, right? I mean, this chair, all of the elements of this chair that are sitting way up here would rather be sitting down there. A lower energy state for that chair would have to be crumbled in pieces on the floor. Likewise, I would like to, be, sometimes I'd want to be crumbled in pieces on the floor, but the physics wants me to be crumbled in pieces on the floor. But my body is constantly investing energy in keeping me upright. There's no energy being put into keeping this thing upright, except for maybe somebody doing maintenance on it when it breaks apart. So things will tend to go towards their lower levels, but at low temperature, it takes an extremely long amount of time for them to reach them on their own. So that's where we get this idea of annealing that's going to start, hopefully, you'll be able to start seeing what folks in optimization started to look at these things and started to realize that there were some really nice optimization analogies. And if they could mimic this system, they could create a really nice optimization metaheuristic. This is also my kind of tacit endorsement for breadth of exposure in education. It's amazing reading the history of some of these optimization algorithms, and you realize that these people that you hear about, like Claude Shannon and Leslie Lamport, the guy who you hear about with LaTeX and things like that, they were so inspired by their general education. So like, for example, Leslie Lamport, and I'll just give this example because it doesn't have to do with entropy. I assume that many of you are familiar with LaTeX, the kind of typesetting tool where TeX was kind of built by Donald Knuth, and Leslie Lamport built a lot of macros to make TeX a little bit more user-friendly. Well, he's a big name in distributed computing, and he came up with a lot of different algorithms that ended up becoming the foundation of many of the distributed computing platforms that we have today. One of them had to do with something called Lamport's clocks, which had to do with when you have a bunch of distributed processes communicating over a network, how do you keep order, like literally order, like what thing happened first? How do you, if they don't all have a shared time, then how do you actually make sure that when you get a message from some other process, that you can order that message before a message from another process and know it actually did come before it, and so on and so forth. This was really important to Lamport. Lamport at that time became familiar with special relativity. And so special relativity is all about the finite speed of light and how much information could possibly be available to you based on distance and the speed of light. And Lamport was so amazed by this idea of these causal light cones. And so Einstein talked about in special relativity that as light goes off into space, it goes off into this kind of cone, and anything outside of the cone could not ever be influenced by that light because it's too far away. And because light is the fastest thing in the universe, then there's nothing else that could influence that thing. So that means that the light cone actually gives you an idea of what two things could possibly be related to each other, like could actually be influencing each other. And the things that were outside of that light cone, you couldn't order. You couldn't say which one was simultaneous because there's no way to actually sort of come up with a way that like how one could influence the other one in a way. And so you could actually come up with an arbitrary ordering. That's kind of special relativity came into play. This is all just kind of background, or this all is kind of like totally tangential from this. But my point is that this was such an interesting idea to Lamport that he came up with this algorithm for ordering things on distributed networks. And that if it wasn't for him just happening to have a background in special relativity, but why would a computer scientist have a background in special relativity? Because at that time, general education, was still a major part of any part of the science curriculum, computer science and all that. So I really do think that just exposure to these ideas, you start noticing connections to your own fields. And so half of what I do when I do bio-inspired design is just gaining exposure to what other biologists do. And then eventually I find those serendipitous connections. So this is another one of those, I think, kind of serendipitous connections. And so when you think about going back to annealing, so I could draw like a graph of all the microstates in a system. And so imagine that on this axis, I've got all the a microstate. So we could order all the microstates. And so I could just plot them all by, the name that I give them. So you can think of these as, or I could say maybe these are our configurations. And I could plot them against their energy. Oh, and I saw there's a question online. I'll get to that in just a second here after I draw this graph. And so the idea here is for a system, we might have a particular energetic landscape here. Let's say it's got some local minima, a global minima, maybe another local minima, maybe more local minima, and so on. And so here I've got this kind of minimum energy configuration. But there are also these kind of traps here where there's going to be, relative to the minimum energy configuration, there's going to be some dislocations. There might be some irregularities. Imperfections, and so on. Now, there is going to be a small energetic barrier that prevents easily getting from one microstate to another. So if I wanted to go from this microstate to this microstate, it's true that the microstate on the left is at a lower energy than the microstate over right, but in order for me to get there, I actually have to increase my energy in order to get up there. And so what I'm hoping you're seeing here is that if I'm at a low, so if I can ask, this distance here, how does it compare? So I'll say less than, greater than, question mark, to K, if I make this a distance here, to KT. And so if you happen to be stuck in this configuration and are at a low temperature, you're not going to have enough energy to make it over this barrier and to get possibly into this configuration. Now, if you are in this configuration, even at a relatively high temperature, you're probably not going to be able to get over into these traps. But if you're in these traps, you might need a high temperature to even get the possibility to go out. Now, if you're at a really high temperature, you can move all over this landscape here. So in this energetic landscape, things, nature tends toward minimization, albeit, let me rewrite that, over very long time horizons. And so basically you can see here that we've now gone from fitness landscapes to energetic landscapes. Where the fitness landscapes, our conceptual model is in terms of maximization, and energetic landscapes, our conceptual model is minimization. But we know that any optimization problem we can phrase as either a maximization or minimization, just with a flip a sign. All right, so that's the picture. Let me see, but I want to make sure that I get, I saw a question or two pop up here online while I have that up there. So I see, so temperature, I'm trying to understand this. So the question here, so temperature decided to what extent an element inside a material begins to vibrate from its normal state, like particles in a system, their extent of vibration when subject to heat. Yes, so temperature, it captures this idea of the kinetic energy inside a material. So at higher temperatures, you have higher kinetic energy, more ability to jump over these little barriers and dislodge themselves out of these states. And then the other question that followed from that was, is the minimum energy configuration E the final state of entropy? We're going to talk about entropy, so entropy is a property of a distribution, not a state. And so we'll talk about entropy. That's an important topic coming up. So hold that thought. There's a question here.
Yeah, I just have a question. This is the one when you said switching from minimization to maximization, you can just maximize and do the negative of it.
Right.
In terms of a fitness function, though, if we were to do that kind of step where we make one negative, shouldn't we also add some sort of offset just so we're kind of like I remember something about the fitness function has to be positive, so we compare it when we're trying to.
Well, you may have to. So there might have to be some offset that has to be added to keep your fitness. So if I want to apply a genetic algorithm, it's very common. I need the fitness to be positive, but the point here is that, there might have to be some offset, but offsets don't matter in terms of optimization. But the idea here is that our conceptual framework is when we're looking at these things now, we're imagining the system is gradually moving towards a lower level. So it's minimization with simulated annealing, but with genetic algorithms, this is like a fitness landscape where they're trying to crawl to a higher level. So, okay. So this is kind of the picture that we have with these physical systems. So like I said, large temperature ensures, so large T ensures exploration, and small t ensures exploitation. And I kind of hate using the exploration exploitation terms here, because as a fundament, there's sort of as someone who is kind of very purist, you can only really apply exploration and exploitation to discrete problems, like in a multi-arm bandit problem in reinforcement learning. But there's a hint of that, and it's a sort of the common phrases to use. So when I say exploration here, I'm kind of referring to global search. And when I say exploitation, I'm sort of referring to local search. All right, so at one temperature, you don't have both. So kind of like in reinforcement learning, where you have a switch from exploration to exploitation, then the thought is that maybe there's a process that allows us to capitalize on both. And in physical systems, that is the annealing process. So imagine you have a surface of ice that you want people to skate on or something like that, but you start noticing some imperfections in that ice. Well, the lower energy configuration would be a smooth surface where the height of the ice would be uniform everywhere. So if you just heated the ice up and then froze it really quickly, you might not necessarily get a smooth surface, because when you freeze it, there might be some sort of, there might have been some wind blowing across it or something like that, where you can sort of freeze kind of one of these higher energy states, as a sort of a snapshot there. So the idea behind the idea behind annealing, so just regular old annealing, is this is a process where we're going to heat the material to recrystallization, and so high temperature. And then we're going to cool slowly, and that's critical here. So we ramp T down slowly. And then we hope we catch the system near global minimum. So this is kind of the purest state. So the idea here again, so like imagine I've got a block of ice, it's got a bunch of imperfections, heat it up, turns it all into water, cool it slowly, and if I cool it nice and slowly, then eventually I'll get ice again. but hopefully that ice will have a flat surface that's just polished. And that cooling slowly is what allowed me to do that. So the heating up, if I was to flip back to this image, the heating up allows, if I'm stuck here, the heating up allows the state of the system to jump to all these other states. Remember, there's just one ball here. It's not a population level algorithm. But then the thing is, if it ever gets into this valley here, then it's going to sit in this valley longer than other valleys because it's sitting at such a lower energy configuration. So if I cool it down slowly, then there's a high chance that I'm going to catch it in this valley. It might sometimes be over here, but it'll be over here more often. And so there's a high chance I'm going to catch it in this valley. And if I catch it in this valley and keep cooling it, then it won't ever have enough energy to get out of the valley, and then it'll naturally go to its minimum energy configuration. So that's the idea behind annealing, physical annealing. And so the idea behind simulated annealing is to do the same. And so the idea here is we build a simulated physical process where the microstate is equal to the candidate configurations. So remember, this could be very high dimensional. So in the case of the physical annealing, then the microstate is every position of every molecule and all of their momenta and all of that. So it's keeping track of everything that's going on inside that chair or this screen or whatever. In the simulated case, we pretend like our microstates are our decision variables all joined together. So our giant decision vector, each element of that vector is now a position or a momentum of a molecule in that chair. So that's kind of the analogy we're making here, is that instead of mapping decision variables to genes with many alleles, we're mapping decision variables to different degrees of freedom that are in a physical system. And once we have that microstate there on our fake sort of physical system, then we anneal the system. So we are going to allow the system to search from microstate to microstate based on that simulated physical process. So just like the ball, as it naturally bounces, just because it has a little bit of energy in it, we're going to put some energy into our simulated microstates and allow them to bounce from microstate to microstate, from configuration to configuration. And that will allow them to explore the decision space. They will if we do the simulation correctly, then they'll hang out in lower energy configurations or minima of our optimization objective. So here I should say the energy here is analogous to our optimization objective, where we want to minimize this. So if we anneal the system, it will hang out in local optima, hopefully global optima of the optimization objective more for longer and longer. And then as we cool it to its lowest temperature, it should hopefully settle down exactly at the global minimum. And so the outcome here is that the resulting microstate at t equals 0 is our heuristic optimizer. So our good enough output of our minimization problem. All right, so that's the inspiration here. This is what simulated annealing will do. We will write out the full algorithm for simulated annealing, but before we can do that, we have to figure out, like, how the heck do we simulate such a physical process? So how do we do this? That's what we have to define first. So in the genetic algorithms, we sort of had to say, well, how do we build this population and have it decide that the higher fitness ones are going to take over the lower fitness ones? And we learned about selection operators and all that and everything. We have to do that, but there's a lot less to do in this particular case. We have to figure out how do we build a method that allows the microstates, the candidate solutions, to hop around in a way that is sort of physically realistic. That's what we're going to do here next. And just to emphasize here, these are not population based. When I draw this diagram, sometimes it's tempting to think about multiple, like I think a lot of people think like, well, there's multiple molecules in a block of matter, and those multiple molecules are running around this energy landscape simultaneously. That's not it. Each one of these dots is the whole chunk of matter with all of its degrees of freedom in one, turned one way. And then this other point is all of its degrees of freedom turned another way. There's only one point bouncing around at a time. If you were to build a population-based simulated annealing, that's fine, but it would just be a bunch of parallel simulated annealers working in parallel without any interaction with each other. So it would not be an evolutionary algorithm. So population is not enough. The idea behind a population-based algorithm, or for it to be an evolutionary algorithm, is that these multiple individuals would have to interact and cause some individuals to be killed off in favor of other individuals. That's what makes it an evolutionary algorithm. This is not evolutionary. It's not even a population-based. But the cool thing that's going to come out of this is we are going to find connections to things like Markov chain Monte Carlo, which I'm not going to write here because we will eventually get to that. Because what's going to happen here is at intermediate temperatures, then this microstate will be bouncing back around, but it will mainly hang out here, but sometimes hang out here. And if you watch where it is at any instant in a sequence of time, so where is it now, that sequence is itself going to become a very interesting population, which will allow us to reconstruct probability distributions, just like you would if you had a population of individuals climbing over a fitness landscape. So that's another application of this. All right, so before we get into then this problem of how do we build these physical processes, are there questions about this? I think I see some new questions online. All right, so does simulated annealing work off of memory at all? There's no memory in simulated annealing. We just have this individual microstate moving to a previous one. So it is possible that it could jump back to some other microstate. But we're hoping actually that there's so many dimensions of these configurations that it's very unlikely for it to, by random chance, jump back to a previous microstate that it's been in before, unless it is a very low energy microstate. So there's no memory in simulated annealing. With hundreds of iterations, can we guarantee optimality? When do we stop the simulated annealer? In optimization metaheuristics, you can never guarantee optimality. If you talk to any of the hardcore math programming guys upstairs, like Jorge Cefaer, for example, they will tell you that they are scared to death of metaheuristics because you can't guarantee anything. So if it is a metaheuristic, like almost all the things we talk about in this class, there are no guarantees you can make. How do you stop the optimizer? It's the same thing. How do you decide on termination conditions for your genetic algorithm? What we'll find out in the simulated annealing is how do you stop the optimizer really comes down to how quickly do you cool the system. And so did you cool the system slowly enough? Because here we know when to stop the optimizer. It's when the temperature hits absolute zero, when all motion stops. But if you cooled too quickly, all motion might stop and you'll be stuck up here or stuck up here. And so how do you know that you cooled slowly enough? You don't, but that's like the speed accuracy trade-off. And if it's a relatively simple optimization objective, you'll get away with running very few iterations of the simulated annealer and be able to cool very quickly and have your algorithm finish. If it is an optimization objective with a lot of things going on here, that it needs to do a lot of exploration and then maybe some exploitation as well, then you might need to let it explore for very long and then cool it very, very, very slowly so the algorithm runs for very long amounts of time. So that's going to be another one of these parameters where you're probably going to have to run this a couple of different times to really trust the solutions that you get out. So, so if the point is to a chair in the energy landscape currently at a local optima, how can it overcome the energy barrier to be on the disintegrated side of the minimum optima over time? Meaning, how can the chair, which is in a local optima, existing in the form of a chair, reach the breakdown state over time? So I think the question is, how do we know we're going to move downhill? So establishing this tendency to move downhill is what we have to build. So just like in genetic algorithms, we had to build selection operators to establish a tendency to move uphill, we have to build a physical simulation that establishes a tendency to move down energetic landscape. So we will build that. It will also have the ability to temporarily move uphill. Just like in our genetic algorithm, we had the ability to temporarily move the opposite direction in our fitness landscape. So we have to build a physical process that generally moves downhill, but has enough extra bounce in it to sometimes be able to move backwards. And that will allow it to be able to get over these humps and then follow these slopes all the way down to the bottom there. So that's what we're going to build. All right. Any other questions in the class then? Pretty clear so far, or pretty abstract? Okay. Now we can talk about entropy. All right, so question here is, how do we simulate such a physical system? All right, so so let's imagine. So this is where we get the. So we're going to be introducing this concept of entropy, which is a statistical perspective on understanding how systems are that are thermally agitated evolve over time. So this is a purely statistical perspective on how thermally agitated systems evolve over time. Hopefully that's readable. So if I were to paint a picture here, so physicists for a long time have been fascinated by the idea that we can tell time by looking at the states of the world. We can tell where there's a before and when there's an after. There's a famous kind of physicist, cosmologist here at ASU named Paul, well, I was going to Paul Davies, but I think Paul pronounced it Davis, but who actually sort of made his whole career on understanding the arrow of time. And so the idea here is that if you have a box and you put some little molecules of a gas or some particles of gas in it, let's imagine it's, or even if it's within another gas, little green, some sort of green gas in the corner of a room. And if you were to alternatively have a box where you had the same amount of green gas, but it was diffuse all over the room, then I think most people could look at those two and say, if you were to show me snapshots of those, they would probably say that this was before and this was after. So in other words, we wouldn't expect a clump of green gas up there to stay up there. We would expect it to gradually diffuse through the room. And we would not expect a diffuse amount, if there's green gas diffuse everywhere in the room, we wouldn't expect it to just hop up into the corner and just, cluster into the corner there. And so if we were to watch a video of green gas clustering up in the corner, you'd say, oh, that video is run in reverse. So somehow the distributions of microstates, that's really what we're talking about here, give us time information. So we can imagine there is a distribution here. So this is a probability density or even a probability mass function of, let's say, positions, to be simple here. So there's another one over here. And there's something special about these distributions that give us the feeling of time passing. And it really comes down to statistics. If you think about it, the reason why we think this is earlier than this has to do with how likely it would be for this configuration to move into this configuration versus how likely it would be for this configuration to move into this configuration. So in other words, if you were to imagine any single one of those little particles, it could move in any direction at any time. It has no bias in which way it's going to, if it's thermally agitated, that means it can just move, any one of these particles can move up, down, left, right at any particular time. So if they're all clustered up there, then there are a bunch of ways for them to move out of that into a different configuration. A bunch of different ways. But there will then, once they're in that other configuration, there's only one way for them to get back into such a configuration. However, here, if you were imagining one of these particles to move left and the other particle maybe to move right, there's a bunch of different ways where in one or two moves, you'd effectively be back to the same distribution. So statistically speaking, you can perturb each one of these particles and you end up in a distribution which is effectively the same distribution you were already in. So there is something sort of statistically stable about this distribution and statistically unstable about this distribution. And that is what physicists believe give us the feeling of the passage of time. This idea of kind of a statistical stability. And so this, and this is captured in this idea of entropy, which is about to define. So are there questions about this? And some people sort of, or are there challenges about this? Make sure here, okay, nothing new online. Interestingly speaking, if you add something like gravity into the mix, then we would, so here in like a room where we don't really worry too much about gravity affecting kind of, we just assume gravity is kind of uniform everywhere, it's holding us down. But if you think about left, right, we don't really think about gravity. Then we'd expect kind of the later distributions to be more uniformly spread throughout the room. If you consider empty space where gravity really matters in all directions, then you don't have these uniform movements. There ends up being a bias in the thermal agitated movements. And it turns out that the uniformity we feel in the room, in space, that's actually tends to be things that look like spheres. And so this is going to end up being the reason why we have spherical planets, but we have distributions inside the rooms that tend to be uniformly distributed. So that's kind of a large sort of connect and extend here. But so the idea here is that we need a concept of entropy, which captures this property of distribution. So we can write entropy a couple of different ways. So I can write entropy here as so entropy technically is it's written as S, and it's actually has this proportionality constant of Boltzmann's constant K or KB. A lot of times you drop that out. So I'm just going to write proportional to instead of equal. And I'm going to say entropy is proportional to this funny little property here. And I'm just going to use log base 2 in this case, but it doesn't have to be base 2 because it's just a proportionality thing, where this here is the probability of being in microstate I, and this is over all microstates. So, and I can rewrite that in a number of different ways. So I could also write this as the expected value, the negative expected value of the log base 2 of all the different microstates, or I can, because of the way the logarithms work, I could actually say, and this is the expected value taken over the probability distribution, or I can write this as the positive of 1 over pi. So for a distribution of microstates, any possible microstate has a probability of being, so if you're a uniform distribution, then that means that if there's a uniform distribution across microstates, then that's going to mean that every microstate is equally likely, and so all of these probabilities are going to be equal. If things are kind of clustered where one microstate is really, really common and the rest of the microstates, even though they're physically possible, are not very common, then in that case, I am going to have some of these PIs are going to be very large and some are going to be very low. And so that case where I pushed all the gas molecules up into the corner, then there are a bunch of different microstates where those gas molecules could be filling the space. But if I only consider configurations where there's a cluster of gas molecules up in the corner, then I've made that microstate, super special, and all the rest of the uniformly distributed microstates not special. And so that is going to have one distribution. Whereas if I just allow the gas molecules to be everywhere equally likely, including sometimes everything clustered up there, but probably very unlikely, sometimes everywhere, and so on, that would be sort of a uniform distribution across microstates. So you take all these distributions and you can characterize this thing called entropy. And you can extend this to the continuous case as well. So there's a way for you to say, if I have a continuous set of microstates, I can take the integral over all my states of the probability distribution of my states times, in this case, the natural log is more common. So the natural log of the probability density, not of position, of state, d state. So this is the continuous extension. Now, what the heck does this quantity mean? So this quantity is basically the amount of uncertainty left in the microstates once you fix the distribution. So this is the amount of uncertainty about microstates after setting the distribution, which in this case is P or F. All right, so what do I mean by that? So if I were to push all of the gas molecules into a tiny little ball, a really tiny fist-sized ball, then I don't give those gas molecules a lot of opportunities to be anywhere else. So they don't have that many degrees of freedom left over. They can be anywhere inside the fist-sized ball, but they can't be outside of that fist side ball. So I've reduced the amount of information I need to communicate where those particles are. And so once I know that they're in a fist-sized ball, then I don't know where they are inside the fist-sized ball, but that's really not a lot of information left over. So there's not a lot of uncertainty left over about where, which microstate I'm in, because there's a very few number of microstates, compressed into that fist-sized ball. If I allow the particles to be everywhere, then sometimes they might just happen to randomly turn up in that fist-sized ball. Sometimes they might all be on the left side of the room. Sometimes they might be on the right side of the room. I don't know. So if I just allow them to be anywhere in their microstates, then that is a high amount of uncertainty. So the idea here is low entropy means knowing distribution tells much information about microstates, or put another way, there is low uncertainty about microstates in the system. And compare this to high entropy, there is high uncertainty about microstate of system. So some people refer to this as an ordered configuration, and this one as disordered. And the second law of thermodynamics can be summarized as saying that the change in entropy tends to be positive, which means systems tend to disorder or higher entropy. So the idea here is if I push all of the green gas in this room into a little ball there, it took energy to do that. So I'm going to do all that, and I'll put it up there, and I'm going to say, I've been here because I'm the only one that does that crazy thing. I put that green gas in there. So anybody walks in the room, if they see the green gas in the little ball, they'll say, Ted was here, because that's his weird thing, is he takes all the green particles, he somehow sucks them out of the air, he puts them in high concentration in one little spot. Ted was here. Now, if I leave the room for a long amount of time, those green gas particles are going to stop being stuck in that configuration. I could run back in, and then I could use a lot of energy to put them back up there, but then they're just going to naturally diffuse through the room. So they will tend toward higher entropy. So they start in a configuration where they all have to be in some fist-sized ball. I don't care whether they're inside that ball, but they have to be in that ball. But they're gradually, without being maintained, will eventually go anywhere they want without inside this entire room. And so initially there was a lot of information. You knew Ted was here if that green ball, gas ball was there. But if you come in and you don't see the green ball there, then I might have been here, but I was here a long time ago. You don't know how long ago I was. Maybe I was never here. Maybe someone else was here. All the information has been removed. So gradually the informational imprint that we leave on the world will fade away into dust. Heat death of the universe. At the end of time of the universe, no one will ever know that we were ever here, because all of that information will be scrubbed from the universe. There is no magnetic tape of the universe that you can rewind to see who was here. At the end of the universe, it's as if nothing ever happened. And that is what we mean by entropy is tends to always rise. It's a statistical certainty that information that is in systems will get scrubbed and scrubbed and scrubbed until you put energy into it to put the information back into systems. So there is something special about these maximum entropy distributions. And that's what we're getting into here. So are there questions about this general idea that entropy is capturing this idea that that low entropy distributions, so this is a low entropy distribution, and this is a high entropy distribution. So if I consider everything compressed here versus everywhere, so low entropy distributions have low uncertainty about the positions of the microstates or about the microstates. High entropies have high uncertainty. See some questions online. Morbid lecture, just kidding. And then people want to know why I am playing with the gas in rooms. All right, so that was just a hypothetical. Okay, so we've got a couple minutes here, so let's give a thought about where we're going to here next. All right, so how many people in the room have heard about MaxEnt methods? So, so I'll just put it up here, MaxEnt or maximum entropy methods. Is anybody is familiar with anybody? It's very popular in the NLP community. All right, so that's fine. So, so the idea here is, so again, this is one of those things where you're an engineer and you realize you have certain constraints. So the idea here is that you have, let's say that you have some, engineer has some information about system constraints. So system constraints, in the case of a physical system, where the walls are in the system, for example, are system constraints. System constraints, and I'll give some examples of this, could be that you are doing, so the NLP example that I'll give here, and I'll probably give this maybe next time, is if you're, let's say you're doing an auto completion. So, now we've got fancier methods to do auto completion, long short-term memory, and all these sorts of things. So, but if you're typing in Google or something, imagine before all of these fancy recurrent neural networks, you type in a couple of words, and you tend to know that whenever someone types, capital I, there are certain words that are more likely to come after that, and certain words that are less likely to come after that. So there's sort of a set of words that are likely to come after I, just maybe based on grammatical constraints. So you can't follow I typically with an adjective. So you can say there will not be an adjective that follows I. So you need to try to come up with a list of words that to put after I in your suggestion list. And so you then say, well, which word should I put up there? And MaxEnt provides the kind of least biased way to come up with that list. So in other words, if you have a constraint, some system constraints, then there might still be a lot of degrees of freedom left over. So then how do you prioritize? And you could come up with a lot of different ways to prioritize, but you're probably going to accidentally introduce some of your personal biases into the distribution. So you say, well, if I know there's not adjectives, I better show the verbs or something like that. So instead, what you can do is you can set up a mathematical problem just like this room, where the walls of this room are the words that are definitely not possible. Those are the adjectives that will never come after the letter I, capital I. You would never say I green, it's unless there's like commas or something like that. But you wouldn't usually have that. But then you allow all of the other word possibilities to be microstates of a system, and you see where those sort of the max distribution gives you a distribution across all of the other possibilities that you can then draw from when you're coming up with your suggestions. So, and I'll give a more concrete example next time, but that's just sort of setting up this. So this idea here is we're going to use the MaxEnt distro provides the least bias in ordering remaining degrees of freedom. And that's where I'm going to end it here, and we'll pick up from there on Thursday. If you have any, I mentioned if you didn't see it, the mini project 2, I extended the deadline a little bit for those of you, a couple who had some debugging things they wanted to work out until Wednesday night. Otherwise, it's probably a good time to start thinking about your team formations for the final project. I'll talk about that maybe a little bit more on Thursday. So if there's any other questions, I have to take those after class. Otherwise, that's all I've got for you, and have a good week. All right, any last questions online?
Sir, for the second mini project, I have went ahead and just defined a small, simple problem where there are ranges of integers that are technically the normal operation conditions or self, and then anything outside gets detected. For that, I had a population of identifiers C in the set C that is set on a specific value. Is this the best way of doing it, or should I